large telescopes with very high resolution data. This is very different. These are small telescopes with large fields of view. They're very complementary to the data sets you've seen. But I was also asked to talk about Mauna Loa, so I really did start at the beginning. So it's a very high-level talk, and then Steve's going to take the future. So Mauna Loa is an NSF facility. It's been there since 1965, operated by NCAR HAO. Our goal is to understand the dynamic release of magnetized plasma, variable solar outputs, and their impacts at Earth. And we do provide the community with unique and, we believe, important observations. Mauna Loa is at 11,200 feet on the northern flank of the Big Island of Hawaii, and that's an active volcano. It started in 1965. It was a smaller building you can see here at the left. That's the original building. And that's the first instrument that was out there, the Mark I K Coronameter, that was moved from Climax. That's Dick Hansen there, recording data. This was the first instrument to record white light coronal images from the ground outside of a total eclipse. And I take that back. It wasn't images. It was the first one to record the white light corona. It took scans, which is that image on the far right is actually an eclipse image. And that red line represents a scan at 1.5 solar radii. So what this first instrument was able to do was to record the brightness of the corona at a height in polarized light, because the sky is too bright for you to see the corona in white light. You need to use polarized light. So these early observations, you're able to build up a synoptic map that you can see there on the lower right. And they recorded 1 or 2 scans a day, and then you can build up a monthly map of the corona. So these were the first observations that complemented the emission line corona data that was available from Climax and a few other places. In 1969, they moved out a second instrument. The Mark II added better signal to noise and additional heights. So now they could provide intensity, again, not images, but they can look at different heights in the corona. And Dick Hansen used that data in 1971, and here's a reproduction from his paper. He actually, in this paper, reports on the first detection of a coronal mass ejection with no imaging. But again, he's looking at brightness. That's a brightness scan that you see. He suddenly sees the corona at different heights getting brighter. And then after that passes, something's passing through the corona, and then it gets dimmer again. And he noticed that this was coincident with a radio burst from Kolgora, which many believed at that time was a signal that some coronal activity had occurred. So now HAO goes on to imaging of the corona. Here's the Mark III instrument. You see 2 coronal mass ejections from Mark III. It operated from 1980 to 1999. It's also a scanning instrument, but unlike the Mark I and the Mark II, it now has a very long one-dimensional diode array that covers the field of view you're seeing there, which is from about 1.15 to about 2.4 solar radii. And so over 3 minutes, they actually rotate the instrument that you see here on the left. That's that round circular barrel. That's Charlie Garcia, one of the first observers at Mauna Loa, standing there in front of it, also a scientist. That thing rotated. It would rotate clockwise and then counterclockwise. And so it would build up an image every 3 minutes. So this was the first time on the ground you're able to get images in movies in white light. During the period of getting images from Mauna Loa in white light from Mark III, HAO added H-alpha. Originally, 1980 through about 1993, it was all on film, which we still have at HAO, and some of it is digitized. And then it became digital after that. And here is what's called the PIX instrument. So now we have both white light corona and the chromospheric activity going on beneath it to try to get a better picture of what's causing coronal mass ejections. PIX had a nice feature of having an occulter that could go in the beam, and it had a narrow band H-alpha filter that you see on the left so you can view the disk, and there's a large filament eruption going off. But then you can move an occulter in the beam and use a broadband filter and track these prominence eruptions to much greater heights than you could normally do with just a disk imager. And so there have been a number of hundreds of prominence eruptions viewed in this data set. All these data, by the way, are available online from the Mauna Loa webpage. Now, here comes the mid-1990s. There's been a number of new instruments in the works, and I should say, by the way, there's been hundreds probably of people who have worked on these instruments and this data over the decade to make this observatory what it's been. So it's a real team effort, and I don't have time to go into all of that. But there were groups at HAO working on the CHIP instrument. NSF funded PSPT, which was part of the Sunrise project, and that instrument, of all the ones I'm talking about today, was actually built at NSO and deployed, one to Mauna Loa, one to Rome, and then the Mark IV. So our earlier director, Tom Holzer, was in the office when these instruments started to be discussed and developed. But then Michael came on board in 1995 and saw these through to fruition. So he was the director and supporting the deployment and the first light of all these instruments. And in order to support the PSPT instrument, which was not going to go on the SPAR, which is the original building you see on the right, where a second dome was added, and that went in about 1996. So I just want to jump to CHIP. I'm going in chronological order. CHIP is also looking at the chromosphere, but in the helium-1 line. And as you know, this data set now also provides information on coronal holes, in addition to things like filament eruptions, prominence eruptions, and chromospheric waves. I'm showing you a picture of Tom Holzer. It's an earlier photo from the 1970s. Tom was the director when this instrument was first developed. And I'm also showing an image of Peter Gilman, Michael, and Bob McQueen. Bob had been the director at HAO in the early 80s, and he was very involved in the CHIP instrumentation. This instrument had a filter that was electronically tunable, so there's no moving parts, but you can scan through a spectral line. So this was a good breakthrough, so you could get Doppler images in helium very rapidly. And so up here you're seeing filament eruptions. There's a chromospheric wave in the upper right that was associated with a flare and a coronal mass ejection. The PSPT was deployed in '97 while Michael was the director at HAO. Now you're getting both photosphere and chromospheric images at Mauna Loa. This provided an unprecedented 0.1% relative photometry to the community. And the goal was to study the variation in solar radiative output as a function of magnetic structures. This was taken over by Mark Rast while he was at HAO, and when he moved over to LASP at CU, the processing of this data went with him. But the data are still also archived at HAO, but LASP delivers the data. And you can see the different types of observations acquired by PSPT. There's blue and red continuum in the photosphere, as well as the calcium line, both in the wing and core. And then the data were used with a model such as the solar radiation physical model, which is also developed in part by Juan Fontenla, played a large role here. What that did is in the far right is identify the different magnetic structures like quiet sun, plage, sunspots, and then track the variability in the radiative output as a function of magnetic structure and solar cycle. So these were very important observations. In 1998, the Mark III was upgraded to what's called the Mark IV. That effort was led by David Elmore, as Michael knows. He was the director at the time. Mark IV offered much better signal to noise. So we're now going from a diode array to an actually CCD camera. There's new optics that were installed. So it had a larger field of view. It has better spatial resolution. And what you see on the left here, in the afternoon at Mauna Loa, the wind reverses flow and it comes up the hill, bringing aerosols with it. And so the conditions degrade typically in the afternoon. Mark III was very susceptible to that. So that image on the left, the cutaway Mark III is on the right, Mark IV is on the left. Because of the enhanced signal to noise, better optics, better detector, Mark IV was able to observe much later in the day. And I'm showing you some images of some mass ejections detected in Mark IV. Now another coronagraph went out to Mauna Loa. This is not a white light. This is the first not white light, not a continuum emission, not a continuum emission coronagraph out at Mauna Loa. This is an emission line coronagraph. This is developed by Steve Tomczyk. He took the CHIP filter, which is an electronically tunable filter, across an emission line, and added polarization optics to observe the forbidden coronal emission line of ion 13 with polarization. And what that provides then is linear polarization, which is produced by the resonant scattering, is sensitive to the direction of the magnetic field in the plane of the sky. And what you see is a comp image there, and that white box is shown on the right just to show you a little bit of the resolution. Those well, they're not arrows, those vectors without an arrow, because there's an ambiguity, are showing you the direction of the magnetic field in the corona in that region, and the length of those indicate the percentage of polarization. So there's a lot of information that you get in emission line. I don't have to tell you that you don't get in continuum. And there's the happy crew after they've deployed comp to Mauna Loa. So the comp polarization provides the direction of the magnetic field in the plane of the sky. Then that reveals magnetic topologies of coronal structures. And to that point, I've got a figure from Sarah's paper in 2017. As you know, pseudo-streamers and typical bipolar streamers that we think of in the corona. A bipolar streamer has the magnetic field pointing in different directions at the top of it, so it has a current sheet going out on top of the cusp of the helmet streamer, whereas a pseudo-streamer does not have that. The magnetic field above this helmet streamer is in one direction, so there's no current sheet. And what's been found fairly recently is that above these pseudo-streamers, you get kind of a hybrid wind that's formed. It's combination, it's some properties of slow and fast wind. So it's important to understand what we're seeing in the corona versus what we're detecting in the in situ solar wind observations to be able to detect what is the difference. Can we identify if this is a pseudo-streamer or a helmet streamer? And this is what Sarah's showing here. She's got a 2D idealized magnetic field of a pseudo-streamer. In the center image B, she's produced a line of sight linear polarization signal that would be produced from this structure. And then she's comparing it to the comp data. And you can see there's very good agreement with these. So the comp linear polarization allows you to detect things like a pseudo-streamer, other than just looking at the topology. You're actually getting the magnetic topology, not just the intensity. So this is much better than we could ever do in white light. This is not possible with white light. And because comp is also scanning the line, the intensity provides Doppler movies and images as well as line width observation. So very powerful diagnostics on both the magnetic field and the plasma. Another white light chronometer was deployed in 2013, so comp and KCOR are now out there together. This is the first imager that we have on the ground in white light. This is not a scanning instrument. It's actually taking images every 15 seconds. With this coronagraph, we put in place a fully automated, just about near real-time data pipeline. So the data are processed within about 2 minutes, and they're put on the website, usually anywhere from 5 to 10 minutes, depending on how fast they get here. But because the images are processed so quickly, they're also run through a CME detection code that was developed at Goddard by Bill Thompson and modified by Mike Galloy and myself, just to integrate it into the pipeline. Chris St. Cyr pointed out in 2017 that this type of a system is really an important component for an early warning system for solar energetic particles. And he points out here that even for the fast CMEs, KCOR is able to detect them about 20 minutes or more before they're visible up in the LASCO coronagraphs. And while it doesn't sound like a lot, 20 minutes, you're also getting the data right away where you have a lag time from LASCO. And that kind of information feeds in, and you can see in the plot down below, this information can be provided, and we do email SWPC as a first potential flag that we have a fast CME, especially on the west limb, and they're be on the lookout for rise in energetic protons and electrons. The other thing is there's, of course, a CME going off and KCOR data there toward the right. And there's additional information you're getting from the KCOR data because it's got such high temporal cadence. There was a very large mass ejection very fast in September 2017. It produced a current sheet way down into the low corona. KCOR is actually seeing into that first scale height down to 1.05. And we saw a series of reconnection jets that have been analyzed, and these are indications of turbulent magnetic fields, turbulent reconnection jets. This data had been combined with some people in the community using also IRIS and AIA. We do seem to be obsessed with coronagraphs, but on the ground, I mean, these data really fill in a gap from space-based observations. That inner image in the circle there, that's K-core, and then the outer image is from the LASCO coronagraph. So there is a gap between the EUV and space-based coronagraph data that Mauna Loa does a very nice job of filling in. It's also looking down in the region where CMEs themselves are forming. It's also an ideal location for observing coronal cavities. These data connect the low corona and with both plasma and magnetic field information into the structures you're seeing in the outer corona and ultimately into the solar wind. And when you see, for instance, mass ejections in LASCO, it's a lot easier to track them when you're looking from white light to white light, as opposed to looking, seeing them in EUV and tracking them into white light. That's sort of apples and oranges, and it's often difficult to track structures from different types of data across a large field of view. And of course, these data also provide information on the variation in energy input, given that there's now magnetic field information from COMP. And I'm going to mention UCOMP in just a minute. I want to point out, though, Michael worked very hard to get MLSO recognized as an NSF facility. And finally, we had paperwork in 2012 recognizing it as an official NSF NCAR facility. And that really led to some major repairs, including a new dome that HAO purchased and NCAR installed. So there were some major renovations and upgrades to the building, which we're very grateful for. Thank you, Michael, because you pushed very hard to make that happen. And some of the other things I could think of was you set up some of the collaborations between us and the USGS, so getting that equipment up there for seismic activity measurements and using HAO bandwidth to get that data down to the USGS. So that's still up there. I mentioned COMP. COMP's been sitting in the optics lab. It's undergoing a major renovation. Steve and the crew have developed, installed, fabricated a brand new filter. There's new optics, brand new cameras. The new COMP, called UCOMP, has much larger field of view. It's going to have better spatial resolution, and it's going to look over a wide variety of coronal lines, from the green line out to 10747. And the beauty of that is that you're now sampling the corona across a broad range of temperatures, from 800,000 sort of coronal hole temperatures out to 3.5 million degrees. This is a collaboration with Enrico Landi, University of Michigan, with HAO. And what you see in the lower right is one of the Michigan models of coronal heating during an eruption. Enrico plans to use these multi-wavelength observations to drive his model, compare it then with the awesome model for the alpha and wave solar model, that is, and to try to get to both understand the observations better and also to advance the model. And Michigan's also going to be producing 3D tomographic reconstructions of the coronal magnetic field, so very excited about that. That's going to be going out very soon. Steve can update you on that. And then later in the year, we have the Cosmo Chromospheric Magnetometer that's going to be going out there. This is an effort led by Alfred Deven. And the goal here is to understand how the chromospheric magnetic field and plasma interact and drive the dynamics of things like prominences, filaments, and other chromospheric structures. He's going to be observing with ChroMag over a wide variety of wavelengths. This is going to produce full vector fields. So he's looking to construct both chromospheric magnetograms, photospheric magnetograms, that's the HI line you all recognize, as well as Dopplergrams. And so this is expected to go out later this year. So we're very excited about, once again, getting chromospheric data, but with vector fields with it. So very exciting. And I'm going to hand off to Steve. The other half of this talk is Cosmo.